Hello, my name is Nathan Jones, and presenting today alongside myself, we have Priscilla Dang, Sadra Tonikaboki, and Sean Lara. The problem our team focused on was using machine learning in order to facilitate early diabetes detection. Our team chose diabetes detection primarily because this was a good starting point to understand the use of machine learning in the medical field, and this is important to us as many of our close friends suffer from diabetes. Diabetes occurs when a human is unable to physically produce insulin or when they are unable to use the insulin they produce. Therefore, it is possible to create a model that can accurately determine if a given patient has diabetes using concentrations of hormones and other external factors. Our model uses a collection of data from multiple patients to determine a relationship between these characteristics and diabetes. And now, to pass it off to Sean to discuss the data used and how we collected it.
Thanks for that introduction, Nathan. Our data was taken from Kaggle. We found two datasets that had the same type of information, so we combined them to produce a larger dataset. Our dataset consists of a patient's medical information that may help determine if they have diabetes. The constraints of our dataset include females that are at least 21 years old, and the inputs are pretty straightforward. However, there are a few details that should be mentioned. The glucose concentration levels and insulin levels are taken 2 hours after glucose administration, and the diabetes pedigree function is a value of how likely you are to get diabetes based on your family history. The output is whether or not the patient has diabetes. Now, I'll discuss how we processed our data. Our original dataset had a few problems, one being that it was a small dataset of 2,000 entries. Another problem was that it was unbalanced. This was because there were almost 2 times more non-diabetic than diabetic entries. This resulted in our baseline model predicting many false positives and not many true positives, as you can see on the confusion matrix. To solve the small dataset problem, we combined two datasets as mentioned before. This resulted in about 2,700 unique entries. However, there were still many more non-diabetic entries. This was solved by duplicating the diabetic entries until the dataset was balanced. This resulted in our baseline model predicting many more true positives. Now, I'll have Nathan explain the details of our model.
Thanks, Sean. We built two separate models for our diabetes detection model. Both models were artificial neural networks using binary cross-entropy loss. We chose binary cross-entropy loss as the core problem of the model is binary classification, i.e., either yes, the patient has the disease, or no, they don't. We settled on 4 layers using a sequential model, 2 layers not including the input and output layers. We determined that using 4 layers gave us the best accuracy we could achieve. Now, we're going to pass it off to Priscilla for the demonstration.
Thanks, Nathan. As for the demo, since we're working on specific types of raw data, we've gone on ahead and created a test set for ourselves ahead of time. I'll be showcasing the results of our model on Jupyter Notebook. Take a look at our test set here. The inputs to our data set will be the following parameters: pregnancies, glucose, blood pressure, insulin levels. You get the gist. And much like the validation and training set, this was taken from the original database, but because the model has never seen a test set before, we can ensure that the results won't be biased. And now let's just give it a second for me to run the results. Oh, here we are. These are the results to our test set. This table here outputs the predictions. If the output value is a 0, then the patient is safe. If the predicted value is a 1, then it means that the model has concluded that this patient may have diabetes. Of course, our model isn't a substitute for a diagnosis conducted by a licensed health professional. Instead, we hope that medical professionals can use these results as an aid for early diagnosis of diabetes.
Now moving on to the results, we can see that on the test data, which was randomly chosen and never used during the development of the model, an accuracy of 97% was reached. Now this would make any man happy as a grade, but let's take a deeper look and see if it's good enough. According to the National Institute of Health in the States, the success rate of a diagnosis in the medical field is measured through sensitivity and specificity, and they are measured with the formulas shown. Taking into account the rates of false positives and negatives, etc., from our model, we can see that the model is both sensitive and specific in the medical definition of those words. Now, the way those two parameters are quantified is the creation of an ROC graph, where sensitivity is graphed with respect to 1 minus the specificity. And the success rate is measured by the area under the graph of when these two parameters overlap. Any number over 0.9 is considered excellent by the medical standard. And taking the area under the graph caused by our model, we get an area of 0.98. And thus, for a medical diagnosis, the predictions of this model are considered very accurate. And the details of these medical standards are provided in the links in the bottom of the slides. Now, it should come as no surprise that the network saw some pattern, as the blood sugar levels of a person that is diabetic could be twice as high or twice as low as a normal person. But what's interesting is that the neural network performed much better than the optimized linear regression model that we had, which was supposed to catch any simple pattern that existed in insulin and blood sugar levels. Therefore, the other parameters, such as the body mass of the patient or its genetic background, made a significant difference. And that brings us to our takeaway message, which is that models like this can not only allow early prediction of diseases, but they can allow us to find parameters that make significant difference to be able to even further prevent such conditions. And here we shall end our presentation. Thank you for your time.